Another draft physics video presentation. Sunday special, we'll call it. I usually take Sundays off. Anyway, there's a couple of videos I think are interesting and worth, reanalyzing properly. Analyzing properly. It's too bad that, there's more and more of these physics type teachers doing physics videos, which is good. The bad news is, though, they're just doing the standard crap that you can already get. So none of them are doing any of this conversation about what if we're wrong, what kind of other ideas could explain the phenomenon. Our evidence, they never concede the obvious, which is the evidence they already have is weak, and they could be wrong. That's just a fact. And they'll just say they can be wrong in some sort of, they'll say it like they're obligated to say it now and then, but they don't really mean it. They really don't appreciate how likely it is that they're wrong. And it's right there in front of them in the sense that they have this huge incompatibility with their different theories, bent space versus the virtual photon and its function. And the only way they can unify it is to somehow eliminate all the causes of what affects things. So field theory to them means pretend the moon doesn't exist and just think about the gravity in the field already. What already is in the field. The speed of light stuff, okay, just pretend it's still there even though the source of it isn't there. The thing causing it isn't there. And they do that with magnetism and all these things by just pretending the force is itself a thing and that the force isn't a byproduct of an interaction with a thing. Anyway, yeah, you have to be already a little bit sophisticated to get the point of the point. But I just mean these are smart enough people to get what I just said and to understand that they are playing sort of a game where all they care about is recognizing how something is affected and not really interested in understanding why or how or what or why the other things in the universe are affecting them. They've just established it as some sort of fact that the thing is this, and they won't go any further in terms of thinking about what it is, instead of just calling it that or this, the force, the bent space. It just doesn't make any sense. It's not an answer to the question of why things move. So anyway, so this is another guy I found, another teacher who's putting up some, brief video clips on various subjects. And, I tend to want to say good, excellent, science is good. But it is wrong. They're teaching the subject as if they've proven and well-established certain facts when they never did the work to really establish them. And it's work. Just like going to trial is work. If you're going to be a lawyer for somebody, you really got to prepare your case. You can't just show up and say, well, yeah, that looks like a gun, and, it's black and it's metally. Maybe it shoots bullets, but, you can't do that kind of shit. You can't just pretend it isn't there. You have to actually deal with the problems they have in their physics. And they don't do any of that. So anyway, we'll play this one. There's a guy called Understanding Physics by Dave. Perfectly decent fellow, whatnot.
So light is an electromagnetic wave.
So light is an electromagnetic wave. Like I said, they really don't have pictures of that, and they don't have any detailed knowledge or reason to believe that. And they already have the conflicting evidence that they're just sort of ignoring this particle duality problem that does exist. That is quantized, and this thing is very difficult to quantize. How do you cut the wavy idea in pieces? It doesn't make much sense. As a mechanical theory, it looks like square wheel. It just doesn't look like quite the right answer. And yet they'll say it as if, we have every single reason to believe. No, they have lots of reasons to doubt, and they just won't do it.
And from GCSE, I'm sure you know all of the electromagnetic waves, radio, microwaves, infrared, etc.
All the sources of radiation. Quantized radiation. okay, in the form of radiation at a frequency. The big difference. So the electromagnetic spectrum is radiation at a frequency. So it's like me showing you a decaying molecule with the stuff jetting out of it, and the stuff jets out in pulses. That's the distinction.
What is an electromagnetic wave?
Right. Well, that you're never going to answer, so you're just going to pretend you're going to give us some insight into this, and there's not going to be an insight into what these fields that you claim exist are, and how exactly something this huge, so this subject is polarization, but I'm betting he's not going to say anything about the fact that the polarization is monstrous. Thousands of atoms worth of polarization, and somehow these thousands, this huge thing is going to affect something infinitesimally small, one electron. It's going to wobble one electron. I don't think so.
It's now the classical view of it, not mentioning photons for the moment, is...
So again, the word photon is kind of broken, because we know that the photon requires there to be a ray length, that there has to be a certain number of those nodes before we can detect it as a photon, and that other instruments, like a frog, can detect shorter waves, and that still other instruments, like a photomultiplier, can detect even shorter clumps, quanta, in a row at a frequency. But it's all dependent on recognizing that there needs to be a frequency to call it a photon. Obviously, a frequency has to be made out of more than one thing. And you can't have a frequency without there being something that is repetitive.
An oscillating electric and magnetic field. On this diagram...
And again, there's no real evidence of any two fields. There's no way to see this magnetic component of a photon. It won't be bent by magnetism. It won't be affected no matter how much I screw around with the magnetic field. I won't screw around with a photon traveling through it, which doesn't make much sense. Doesn't make any sense, frankly. What there's evidence of is a frequency travels through space, and that it has a certain linear. It has a certain width, and the width is made out of alignment in one dimension. Okay, yeah. So, so that's worth talking about. That's worth drawing about, let's say. I think there's enough light here, yeah. So, as I pointed out, like you could take a surface and you could think of something coming into the surface as a row of things, and that they're going to bounce off. The first one bounces off first, and then this last one bounces off last, and they end up just inverting their positions. They turn, essentially. So what was on the top before ends up on the bottom. What was on the bottom ends up on the top. That's one way to think about polarization, is that it happens over a length of space. Another way to think about it is the antenna argument. You could argue for other forms of electromagnetic radiation or photons, is that it's really just about how far up the signal, the frequency, can go up an antenna. Okay, so the length of the wavelength would essentially be the length of time you have to go up the antenna before you have to hit another pulse. And that would tell you like a 3 gigabyte stream of radiation can only get a little bit up the antenna before the next gigabyte, before the next bit, the next quanta, the next lump of the wave. And that's why it only needs a short antenna, because this extra antenna will do it no good. But the slower I make the frequency, the longer the antenna needs to be for me to have a really good chance to maximize how much signal I can produce. Now I could have a smaller antenna with a slower signal, but it means everything has to flow out of here and nothing can go up the antenna and flow out here. And there's an advantage to increasing the volume of space. You can flood your frequency. You can put your frequency in more space if you can get further up the antenna before your next pulse. So that's a way to understand how light is produced also, that it's produced by crystals in the material, and that what you're really doing is essentially bending the crystals. The crystals are changing shape, and that change in shape in the crystals is what's creating the frequency, and that change in shape is linear. So in any one direction, it's changing shape, or allowing electricity to migrate through the crystal and change the crystal progressively a certain amount based on the wavelength of the light. So it's a very small distance you can go when you're talking about a nanometer's worth of wavelength. So the quicker the frequency, the less space can produce the radiation. The less atoms, the fewer atoms that will be involved in producing the radiation. Okay. What we call the radiation, and the radiation is really just reflections of pressure. How the pressure bounces off a surface depends on where the surface is. If the surface is here, the pressure bounces off different than if the surface is here. Okay. Continue.
I've got the electric field as being vertical and the magnetic field as horizontal, and they oscillate at right angles to each other, and both of those are at right angles to the direction of propagation, which is
so anyway, they're saying this again, like they have a ton of evidence indicating this is how it works. Now, the fact that there's a right angle condition, the right hand rule essentially, in the interactions of electricity, charge, and monopoles and dipoles, and how they interact with each other. Yes, it is a fact that some part of electromagnetic theory must account for the fact that energy can go in one dimension and it comes out in one of the other dimensions, perpendicular to the way it went in. That's a fact. There's a mechanism that causes it, though. It's not built into the photon. It's built into the force itself.
Basically, the direction that it's moving in. And in a vacuum, the wave travels at 3 times 10 to the 8 meters per second, and that's little c, and that's the speed of a light or any electromagnetic.
So again, nice information, but again, it doesn't really deal with the fact that we do know that speed of propagation changes depending on the medium that the light has to travel through, and that there's every probability that the energy that goes in is a little different than the energy that comes out, that the actual quanta doesn't travel through the medium, that the quanta of energy, the impulse, is transferred to these much bigger objects, electrons and protons, and it must move them, and that's what's slowing it down in a medium. But none of that context will be offered.
Wave in a vacuum or in air, it's pretty close to that. 3 times 10.
So the key thing would be is air is transparent. Okay, the molecules that make up air are transparent atoms, and they are not dense enough to cause any significant slowdown, in the sense that the photons getting from me to you don't have to interact with very many atoms, and therefore they don't have to spend a lot of time moving electrons and atoms.
To the 8 meters per second. Okay, you must be able to use this equation, V equals F lambda, or C equals F.
So it's kind of a silly question, a statement, in the sense that there is no difference between frequency and wavelength. They're measuring the same variable. They're just measuring inversely. One based on its length, and the other one based on how much of it passes at a certain amount of time. So that one of them is a timed element, frequency, and one of them is a length element. And so you're just creating an artificial standard to C that you're measuring it against a standard amount of time. So obviously the frequency would be the same standard that a clock runs on or any other thing. So yes, the answer will be C because of contrivance, not because of any fundamental facts that frequency or wavelength has anything intrinsically to do with the speed, except for the fact that everything that you're going to time is going to be timed based on a standard that C is the standard for.
Lambda for an electromagnetic wave, And I suggest you pause the video and do these, and I'll show you the answer in 5 seconds.
I don't think he does that, but okay, yeah, there's the answers. Blah, blah, blah.
Now,
Who cares? Okay, so now we're on to polarization, finally. Okay, but he's gonna make some statements that, again, just haven't been proven, and they just state. I mean, this is how they're teachers. This is teachers talking. Okay, it's not like it's the students; it's the teachers, and they say things that they just have no business asserting as fact.
Polarized and unpolarized. Now, a polarized wave, the electric field oscillates in one plane only.
So this is where, you have to make a distinction between a group of photons, like a mass of photons, like there's 1 and 2, 3. I'm sending like 20 at the same time or something. And you would say that all of the photons I send are of the same orientation. That is, the electricity all went in the same direction through atoms and created an impulse all going in the same plane. They're all polarized in the same direction. They're all length polarized, right? So you can sort of understand that, like if I shot electricity through a semiconductor or an LED or something, that it would make sense that the electricity passes through the conductor in a certain rate, and that the photons, the little bits of energy, will be created as the electricity moves through the conductor, and that there'd be a plane that all the little blips would be on, the wave blips, if you want to look at them that way. And so I can have a system where we already know that the directionality of the impulse that's creating the light, or you can have a system where you have a whole bunch of different LEDs, a whole bunch of different ones with electricity going this way and electricity going that way, and they're going all kinds of ways. And so the photons are being created on all kinds of different planes. They're from the movement of the electricity. So like the sun, it's creating photons that are still all in one line. They're still flat. Okay, they're not polarized in all directions, one single photon. Each photon has a plane of polarization, and you're just sending a bunch of them, and they all have random, quote unquote, polarization. So that would be unpolarized in the sense that they're not of one orientation, where if I create a mechanical system to produce light, it'll all be of one polarization because it's all coming to you from the same mechanism. So like reflected light, glare, all the sunlight that hits to make that glare is all hitting across a surface where it's all coming down at an angle and then bouncing off. And so it all has the same polarization because it's going through this flipping process, you could argue. So it all has the same polarization because that's the only way the surface can send you coherent light. If it's got the wrong polarization when it reflects, it will reflect in such a manner, the little bits, with an inconsistency, and then you'll have deconstructed photons and you won't see them. So the only ones you'll see are the ones that hit the surface and reflect in one direction rather than disperse or scatter.
I ask my students so many times in tests, what is meant by a polarized wave? The electric field oscillates in one plane only. If it's an unpolarized wave, then the electric...
So he's saying a wave can be unpolarized. So I would argue that it's nice to think about, but I don't think there is any such photon, because then polarizing filters would block a tremendous amount of light. If there was such a thing as all these mixed polarizations, then only a tiny percentage of light could get through one filter. But anyway, continue.
Field has components in every plane, or you could say it has X and Y components.
Right, it sends photons of all different variations, but each photon is one straight line.
Okay, it's all over the place. The E field is in all planes. Of course, this is still perpendicular to the direction of propagation. Light from the sun is unpolarized. Light from a filament...
So you could argue that light from the sun is multipolarized, would be, I think, a more accurate thing to say. The photons are polarized in all planes.
bulb is unpolarized. Now, polarizing filters, they will absorb one of the planes.
Okay, so he said the word, they will absorb. Now, I fell for that for years. That's what I thought too, because they always do it with these drawing the lines. And they use examples like in radar, they use actually a metal grid to actually absorb energy. So you get this impression of how it works, and it's not accurate. And I did think about it years ago about how, I had a piece of polarizing film, and I was saying it doesn't really feel warmer. It doesn't change any when I send a lot of light through it. So it doesn't seem like it's really absorbing any amount of energy. But I didn't know what to do with that observation, frankly, and I never saw it tested anywhere. I didn't have any reason to believe that this story was different than what you're told. And the truth is, if you look through a polarizing film, yes, it's a little darker than normal light, but you can understand that it really isn't bars. It really isn't opaque stuff and then transparent stuff, and opaque stuff and transparent stuff. If you look through it for a magnifier, it won't look like opaque next to transparent. It's all transparent to some extent, and all you're really doing is making one section a little thicker and then thinner and then thicker and then thinner. And the thicker and thinner part are just doing the changing the phase of the light by slowing it down a little bit more on the thicker parts. You're breaking the phase of the light, and so you didn't absorb the energy, you passed the energy through. It's just that you've broken the phase of the individual quanta that was the ray of light. So now the ray of light has pieces that went through the double layer and pieces that went through the single layer. And now the pieces are out of phase. So the light goes through, it just gets knocked out of phase, which makes it unreceivable by the antenna that is your eye.
So if you have some unpolarized light and it goes through a polarizing filter, then it will absorb one of the planes. In this particular case, the first filter absorbs the vertical plane and lets the horizontal plane through. Then if you...
So that's what he says. So that's their theory. I would argue that it's likely the other way around. The vertical is the one that passes through, and the horizontal is the one that has big problems in terms of it's got a lot of more bits out of phase. So the one going vertical has a chance of getting through the bars, like it was a frisbee, and the one going horizontal can't get through the bars. And then as you bend it, you can get more or less in. So obviously half the light can make it, because anything like this will go through, and anything like this will get blocked. So half the photons get catastrophically destroyed and half remain intact. Now the real truth is that some of the ones that you break going this way you can repair with some of the ones from this end, because you're changing phase. So you take a photon that was damaged that went through this way and got damaged, and you're really going to take pieces from one that went through this way and got damaged, but the two are now back in phase. Pieces from this one have the right phase to match up with the pieces from the other one, and you end up making a real photon again, back in phase. So it's really all about phase. All you're doing with the filter is phase shifting.
You have another polarizing filter that absorbs the horizontal plane.
So there's no absorption. There's just changing phase. That's all the filter does. So the first filter takes some of the quanta. I mean, really, I've drawn this so many times that it's really kind of horribly, awfully, terribly redundant to have to, but I'm doing this particular video, so I'll make the argument. So the idea is the quanta, or the nodes of the wave, however you want to look at it. This is where the nodes are. What's happening is when you go through the double layer, see, these photons aren't in perfect alignment. So the point is they're out of alignment this way, and that's its polarization. It can be this way, it can be all kinds of ways they're out of alignment. But they're out of alignment in a line. Just like this, in a sense. Just like this two-dimensional out of alignment. And so part of the light, part of these little lumps, one of them goes through the 2x layer, where it gets twice as phase shift as the 1x phase shift of the material. And so now this photon is here instead of there. And now you don't have the frequency. You've broken the frequency. The energy's still there. And so you can imagine that another photon went through, and instead of this bit getting hit, this other bit up here got hit. And by knocking it back to this location, right, now you have that frequency back. Now this photon's broken, but you have this one's whole again, because you took a piece in the right place and you moved it the precise amount to restore a photon.
And then nothing would get through. We call that cross Polaroids.
Right, so that means that you've broken the phase so much. You've taken the pieces, this way, and now you've taken pieces this way, and you've broken so many. You've got so many pieces out of phase now, you just can't reconstruct any photons because the phases have been knocked in opposite directions. Way too much. Way too out of phase to put any of the pieces back together.
You can obviously test if light is polarized or not by looking at it through a polarizing filter. And if you turn the filter through 90 degrees, it should get lighter and darker.
It will. Yeah, that's a fact.
Interesting that light that has reflected off water becomes polarized. And if you...
So I should have said that. I said glare, but it's glare off specific surfaces. And so you could sort of make the point that water is a specific kind of surface in terms of its flatness, and it's there's probably some other thing. I won't speculate, but you can understand why there'd be a mechanical reason why it would have a preference for certain light coming in certain angles will retain their order, their phase, where if they come at other angles, their phase will be destroyed by the fact that the water has a molecular surface, a geometry.
Look at light reflected off water through a polarizing filter and turn the filter, it gets lighter and darker. Uses of polarizing filters. Photographers use them to cut out glare, which is light reflecting off water. LCD
are other surfaces, shiny surfaces, obviously, smooth surfaces. So I don't know. Yeah, these are all facts, that you can use polarization. So the real argument, though, is what is the polarization? And what is this thing we're seeing? What are we seeing? Are we seeing something that was always a continuous thing? Or are we seeing what you can put together of the stuff that's in the field? And my argument is there's no real such thing as a single photon gun. There's no real way to ever produce single photons. That this is just energy, and you can have a lot in one location and just one piece in the other location. Therefore, you only see one photon. So you can have like 20 quanta here, and you can have 1 here, and you can have 50 here, and you can have 5 million here. It's still one photon. And so the photon is dictated by a consistent frequency hitting numerous electrons. So it's a collected bit of energy. And the reason why crystals are so good at converting that energy is because they're crystals. Okay, because they share knowledge with each other, the atoms, about what's hitting them, what's hitting their electrons. And it's able to be conveyed to another surface or converted into electricity. So it's transparent, or it allows to take that ordered frequency and convert it back into a flow of electrons in a direction, a right-hand turn. All right, that's probably enough of that. I don't
Displays, for example, on your calculator, there is a polarizing filter in there. 3D glasses in cinemas. When you watch a 3D film in a cinema, you're actually watching 2 films. And one film.
Right, and so the key to 3D glasses has been explained by a few people is all they do is put one clear layer. They put an extra layer of clear film over one of the lenses. And it's there for one purpose, to create another phase delay, a phase shift. It doesn't do anything else. It just phase shifts the light. It slows it down a little bit. So the frequency changes. The placement of the quanta within the frequency is changed by the delay you're creating in the progression of the light. So you're changing the phase. You're not filtering it. You're not blocking it. You're not absorbing it. You're phase changing it. And that's it. It's just all phase shift.
Film goes in one eye, the other film goes in the other eye, and they are separated using polarizing filters. And it's also used for stress analysis in components, and I mentioned that because there's a pretty picture of it happening.
Yes, usually with thin film materials, different substances that will allow for internal reflections, and then you can see the material's alignment, its geometry of the atoms even, based on how the light reflects. Alright, so that's enough of that one. So we'll do one more video. 5 rules of the electric field. Like, this is from UCLA physics video. So again, I'm just playing this to point out how, this is the jargon, this is what they teach. And I'm arguing they're teaching something that I think there's plenty of good reason to doubt it as the truth. And they just don't admit that this is a thinly evidenced theory they're promoting or propagandizing to be an absolute truth.
Learn the 5 rules of the electric field. The electric field is a force field that fills space, pushing and pulling on electrically charged objects.
Right, and doing no different than gravity, except the electricity can have both effects. It can attract and repel. But it's obviously the same kind of mechanism. Stuff moves, and it moves for a reason. And the reason is something changes in its environment that it's sensitive to. And I would argue the only sensible way to create repulsion and attraction is to understand that electrons and protons have to be interpreting something differently, fundamentally differently. And that interpretation really is dependent on the thing being different too, because you can't have the inverse thing. You can't have attraction and repulsion without having two things that change. Not just the electron and proton, but the force they're interpreting also has to be a dipole field. You have to have both to be able to create the 4 different reactions. The attraction, repulsion, attraction, repulsion. To create 4 different reactions, you need more than just 2 things to change.
Rule number 1. Imagine this red ball is a large positive charge. Now we can test out the electric field with a small imaginary test charge.
Right, and we could just imagine another little blue ball right next to it, negative, and just pretend they don't discharge, and then say, well, what would a little tiny test charge that looked just like that with a little blue and a little red one, what would it do? And it'll do exactly what a magnet does. And again, they are saying these aren't the magnetic monopoles.
This is also positive. As I bring it nearby, you can feel the repulsion up close. A little weaker with distance.
I guess they're doing this for high school kids or something. I don't know. It is fairly patronizing, this pretending. Thank you for pretending for me. He's clearly pretending.
And on the other side, we also notice a repulsion. Positive repelling positive in every direction.
Yeah, and why would it do that? Magic? So they don't have any reason why it does that. They just say field. I would argue that the reason is that obviously there's something that reflects off red things. And it gets caught between 2 red things. So when you bring more red things together, there's stuff caught between the 2 red things, and it keeps bouncing back and forth at the speed of light, creating the inverse square law, an increase in pressure. As I get closer and closer, the pressure gets twice as much. And we know that twice as much, in this close circumstance. But we know it would be, if we there's no point in reversing the circumstance. But clearly, if there's no way for the stuff to go anywhere between the two objects, it would be half the distance, twice the pressure.
And that's all the first rule is. The arrows show the net force on a small, imaginary, positive test charge.
Right, so it's all imaginary stuff. But they know that they don't have to create an imaginary charge. He just did it in the beginning there, right? Where he took a little paper ball and he charged the whatever it is, vulcanator. And he made his charge, and he took something else with the same charge, and he saw the attraction. So you don't have to imagine it. You know it's there. And you know there's something real that's caught in between those things that just isn't allowing them to get close.
Rule number 2. Electric field arrows point out of positive and into negative.
All right, there's no electric field arrows. So again, I'll just do the line of force, lines of force versus field line kind of argument. And that all of these things should be understood. And the fundamental Gaussian style mathematics sort of dictates it. They should all be understood as just having radial lines of force from them. They radiate lines. And depending on the charge, the test charge, okay, it either is repulsive to something else or it's attractive. So if it's a minus charge, in this circumstance, it'll repel. If it's a plus charge, it will attract. But it does so based on even pressure created by radial lines. There's no lines that go from this object into this object. That's just a path that something can take if I put it in a field. But that's the path it takes. It's not the force acting on it. The force is just radial from all the objects, and that's why there are R rules and R squared rules and R cubed rules. It's because of that principle. Radiation. Symmetrical radiation.
Out of positives and into negatives. But of course they do. That's the direction a positive test charge would be forced.
Right, and a negative test charge would go exactly the opposite way, making it clear that there's more to this equation than just saying the word force, because the force clearly it changes inversely. All I do is change the color of these objects, and I get an inverse reaction.
Out of positives and into negative.
Right, and that's only because he's chosen to say, I'm going to test it with a positive test charge. If I tested it with a negative test charge, it'll go in exactly the opposite direction. So this is just, there's no such thing as these arrows. They don't exist as a force.
Out of positives and into negatives.
So if he wanted to do that correctly, again, he would say, this is radiating a proton repulsive force. This is radiating a proton attractive force. And just understand it as that. But that these are all straight lines. There are no curved lines in the force. The force is all straight lines going to infinity.
Out of positives and into negatives.
So again, this is where they allow mathematics to break rational modeling, because it's only because of how current moves through wires that this is the direction they've put on these arrows. Again, he's testing with a positive charge. It's an arbitrary selection. So all those arrows are really straight lines, leaving perpendicular from the surface. Radial, straight lines. That's what the force is doing. And if you put something in that force of radial straight lines, it will move on those paths. That's how it will move. But it's not how the force acted on it. And the same is true for gravity and all the other things. The force is radial. If if you had a sail and you could sail based on how light hits you, you would behave the same way, navigating between suns, for example. Or, I can't make a sun that pulls light in, but, if such a thing was imaginable. And all you're doing is following the current. You're following which way the wind is blowing. The light is flowing.
These other far-off lines will just keep on going to oblivion.
Yeah, all of them go to oblivion. The lines do. Okay? There's no force on those lines, following those lines.
Rule number 3. Line density is field strength.
So now he's drawing straight lines. You see the inconsistency here? See how they just make a mess out of this? So now he's really going to be talking about the force, right? He's not going to talk about what a test charge does. He's going to be talking, because he's got it, it's made perpendicular. And he's going to just talk about, now this is line density. This is what the force actually does. It radiates. And he could draw 4 lines, or he could draw 8 lines, or he could draw 16 lines. And the fact would be, as you want to be totally accurate, he would have to draw 1 trillion lines. Okay, but they're all doing the same exact thing. They're radial, perpendicularly leaving from that spherical surface.
That is, closer lines are together, the stronger the electric field. For example, if I add another positive charge to this glob of charge, it will increase the number of electric field lines, doubling the strength of the electric field.
And again, he's just representing it with 4. He's saying 1 charge equals 4 lines, 2 charges equals 8 lines, 3 charges equals 9 lines. He's just doing the obvious.
I want you to notice
12.
that the space between the lines increases. That is, the further away you get, the weaker the field is.
Right, but more importantly, it's increasing in 2 dimensions. The lines are separating from each other not only this way, but also this way. And that's the inverse square law.
If I add yet more charges, we have to add yet more electric field lines. You can witness the electric field in action when using a plasma ball.
So he really didn't say anything about the fact that that's a 2-dimensional drawing, and to accurately represent the actual divergence, you have to cheat a little. You have to have them separate more than they really do to duplicate the inverse square law, because they're separating in 2 dimensions.
The electric field around a plasma ball is strong enough to ionize mercury.
So again, all he's really saying is the voltage, all right? So it's just voltage, the voltage difference between the ground going through his hand and the electrical potential of the surface of the glass is a high enough voltage to conduct, to force the gas to be conductive.
Neon, helium, and even the air itself. Here, I'm helping the air get ionized with a conductor, a penny.
Yeah, well, the conductor is the atmosphere itself, right? So the conductor isn't. So I'm just saying, in this case, the conductor isn't being. The fact that the penny's conductive is necessary, but the real point is he's collecting more electrical potential over a larger area and making it possible to create a greater voltage difference. So he's giving a place for the voltage to increase, like putting a point on a stick.
But the effect weakens with distance.
So, that should be something you explain with a little more reasonableness, like saying just like a light bulb, just like a lot of other things that obey the inverse square law, this capacity, this voltage will diminish because they're individual rays coming off of an object. And just like the sun, if you're a foot away from the sun, you're going to get hit with a lot more photons than if you're 2 feet or 4 feet or a million miles away. A lot less photons can hit you.
Rule number 4. Electric field lines never cross.
So again, electric field lines and the concept of lines of force. So, to me, those are distinctly different things. And one of them should never be understood to be having any force traveling on it, and the other one is the force. The force is doing this. Lines of force are radiating from objects that have charge and radiating by strict laws and doing this perpendicular thing off the surface. So if you assume spherical symmetry, it will produce an inverse square law.
Imagine two positive charges. The net force on an imaginary test charge would be this.
Well, the fact is, so he didn't draw that very straight, but obviously this will be a straight line. That's one force. And the other force is going to be another straight line force. And yes, the outcome, it's going to be interpreted by the piece of matter. If it's getting hit with the two forces at the same time, it will do the math and say, what are these two forces equal? Well, this component and this component are going to cancel, so that won't exist anymore, and all there's going to be is two things moving this way. Two forces pushing that way.
And this. That is, two electric field lines. Crossing? No. The net...
They would cross if you didn't have an object there to interpret them. So, yes, they do cross. They cross all the time, and it's completely irrelevant because they don't interact. Forces don't interact with forces. Lasers don't crash into lasers in any way that changes the universe. They might interact, but they don't interact in any way you can see, just like if I was to create photons that can move the speed of light, little balls, and I smashed them into each other and they perfectly reflected. That is, they didn't lose any time and they just changed direction. You wouldn't be able to tell the difference between two of them hitting and two of them missing. The universe would look exactly the same if they missed or if they hit each other. Fact.
Force would be in the horizontal, as the two forces cancel in the vertical.
I mean, you could have drawn that more simply. The vertical component goes this way, the other one goes this way. Those two forces put end to end equal 0, right? No advancement, 0. And also all you have is that way.
Leaving a resultant electric field horizontally to the right. Rule number 5. Electric field lines are perpendicular to the source and the terminal. That is, they always come out perpendicular to surfaces that are positive and enter perpendicular to the surfaces.
So again, they don't enter. And obviously, as you get closer and closer to an object that has like a drain, I could put a piece of dust in a drain, right, a floating object, and you'd see it swirl and do all kinds of things. Now, there's no force causing swirl. It's just a combination of forces. So, of course, when the thing's getting really close to the drain, it's going to start going in a straight line right for the middle of the drain. So, yes, it's always perpendicular. But you could make the same argument that light comes out of a light bulb by the same principle. It's coming out of a point source. A small little thing is creating light in a big giant circumferences. The circle I am from the light bulb could be a 10-foot radius. It's a gigantic circumference compared to the actual filament that's burning.
That are negative, perpendicular at all times.
This perpendicular, and that just sort of points to the argument. It's perpendicular because that's what the actual force is. Perpendicular. Force is moving in straight lines. It's perpendicular because the force is a straight line.
This can be seen in these lettuce seed demonstrations. Soaked in vegetable oil are little lettuce seeds, and each side is getting charged oppositely.
So it's just like they're getting magnetized. It's the same concept, and you're seeing the same effect, is that when they get into rows with each other, they're not going to stick to each other because they're essentially oppositely polarized. One end is positive, the other end is negative. They're like a magnet. They have the same polarity. And so they're going to repel each other, because if I made myself red on top and purple on the bottom, you know, that's half of me on my torso, and I walked up to another person who's red on top and purple on and blue on the bottom, we're going to repel each other because both of the red ends are going to shoot red repelling stuff, and the blue ends are going to shoot this repulsive stuff, and they're going to repel. But if I invert it, if I walk on my hands, then all of a sudden, yeah, we're going to stick to each other. That kind of logic. And they're obeying the same rules here. It's the same rules as magnetism.
You'll notice the electric field is perpendicular to the conductors, even if the conductor is just a single point charge. Notice also that the electric field is 0 inside of this conductor.
Okay, so again, this argument that the field is 0 inside the conductor is another statement that just really isn't accurate. It's not a 0 field, it's a net 0 field. So, and just like with gravity, so if I made a hollow Earth, right, there's this simple argument that I could stand here and there wouldn't be any gravity pushing me, even though I got a mass right under me. There's no gravity here. I just float around. It's completely nothing. There's just no gravity on the inside. And the simple argument is it's because the force is affecting me more from all of these angles, even though it's weaker, its effect on me. There's more of it. And there's this little tiny bit of surface that I'm affected by here, but I'm really close to it. So it's just really just saying that this close force is the same as this amount of far force. And the two are always going to be the same. So no matter where I go, it's always going to be equal. So there's plenty of force going on. There's plenty of action in here. It's just that it's always going to be inversely proportional. There's going to be as much as I'm close to this, I'm going to be just as much density from the stuff I'm far away. So the closer I get, the less I'm exposed to, and the further away I get, the more I'm exposed to, and they're inversely weighted. So it always ends up being a net 0 in effect, but there's plenty of force.
That is, there are no lettuce moving. Review. As a review, consider these two charges, one positive and the other negative. This one's twice as charged as the other one. Now the lines must go out of positive and into negative, but the twice as charged one will get twice as many.
So this is just the test charge lines, the lines of the certain boat I put in here. This is what a certain kind of boat will do. And if I put a different kind of boat in, if I put a boat that was a dipole, blue end and a red end, the boat's going to turn. It's going to do all kinds of things that are going to be very different from the test charge.
Lines.
So at least he's got that
as
part
the negative
right.
one. But the negatives lines will go into it. Now the electric field lines can never cross. So these ones have to travel to meet these ones. Notice that they're all exiting perpendicular.
So again, this is just arbitrary. She's going to draw maybe two of these lines going into the same place. The end point can be the same place, but the fact that they don't cross is just an example of the fact that how could they? Again, if it was wind or any other thing I was talking about, of course the lines can't cross. The thing in the stronger current can't move the bigger arc. So obviously those arcs are always going to be inside the other arcs. There's no rule that they can't cross except the logical rule that there's no circumstance in which the thing being affected by less force can travel the path that something being affected by more force is affected by. Certainly can't draw a straighter line than the one going straight from one surface to the other. So really not a meaningful drawing in any real respect.
And now that you know these rules, you can draw any electric field. Good luck.
Yeah, horseshit. So anyway, so there's nothing to say that this wouldn't come in over here eventually, because it would. But anyway, no need to argue it. And that this one would bend, maybe not at all. You know, it would just end up going, you know, bend in the beginning, and then it's free. It escapes any influence because it's just going too fast away to ever be affected by the weak force. But anyway, enough of video and such. So till the next time, and so forth and whatnot. And these, you know, these are necessary corrections. And again, they're just saying all this stuff based on the fact that they've created a whole regime, and this is how. You know, they don't think about it. They've just accepted what somebody else says as a starting point, and that's their position. And they just never look back to say, well, maybe I should fact check. It's like me being raised to be a blacksmith or something, and I never consider any other choice because somehow they told me I'm supposed to be a blacksmith, and I just never even think about, well, maybe I can do something else. Maybe I'm better at something else. It's just really stupid. Yeah, that's what it is. It's like just breaking one of the rules of intelligence is to keep that open mind thing working. Keep yourself receptive to change and modification because mistakes are possible. Anyway, till the next time.